Okay, so welcome to week 5 problem solving session. I am Shreya, one of the TAs for this course on probability and statistics. So today I'll be discussing a few problems based on the concepts that were taught to us during week 5 lectures. So before moving on to the problems, I would like to brush up on the concepts a little more and then move on to the problems. So first things first, let us first have a recap on what was discussed during the week 5 lectures. I hope I am audible and I shall start now. Alright, so firstly, we discussed what do we mean by a random vector. So initially we had learned how to use random variables, or we learned about random variables one by one. So in a single variable case, what happens, we learned that. Now we are going to focus on how to analyze or how to find distributions when we look at two or more random variables jointly, and hence this concept of random vector was introduced. So we have one sample space. From here we have the elements, that is omega, and if we can find a mapping of omega onto the real line given this omega script f and p being the probability space, then x1 and x2 are the random variables. Now if we have two random variables together, we would for each omega we would have a point in the 2D space. So similarly, if we had d d elements in the random vector, then we would be looking at a point in the dth dimensional space. So this is very useful in real world situations when we have to model two or more random variables together. So we learned about how to represent the CDF of a bivariate distribution when we have two random variables. So this was given by this: capital F of x1 and x2 equals to probability capital X1 less than equal to x1 and capital X2 less than equal to x2, where x1 and x2 range from minus infinity to plus infinity. So as I was saying, probability that an omega belonging to sample space such that the mapping x1 is less than equal to x1 and x2 omega is less than equal to x2, where omega belongs to the sample space. And also we learnt about a few conditions that a multivariate or bivariate CDF should satisfy. So this fx1 x2 should be non-decreasing and continuous from the right with respect to each x1 and x2 coordinate. Limit both x1 x2 tends to infinity, f of x1 x2 should be 1, and if either tends to minus infinity, then it should be 0. And also we learned a very important criteria that for every a, comma c and b comma d, where a is less than b and c is less than d, we should have this criteria should be satisfied. So fbd is this whole area between, so marked in black, that is fbd. From here we are taking out these small sections, and this small area where x1 will lie between a to c, a to b, and x2 will lie between c to d, this area should be greater than equal to 0. So this is an very important criteria or condition that the bivariate CDF should follow. Okay, then we learned how to represent a joint PMF. This is not a PDF, this is we can write it as a PMF for a discrete case. Okay, so for a discrete case, if we have x1 and x2 a two-dimensional discrete type of random variables, then the probability mass function is given by probability x1 equal to small x1 and x2 equals to small x2. This is called the joint PMF. And if we had to find out the marginal distributions from the joint PMF, all we have to do is we have to take summation over the other one. So if we are to find out the marginal distribution of x1, then we should do a summation of the joint probability for all values of x2. Similarly, if we want a marginal distribution on x2, we should take a sum over all values of x1, and we should sum up the joint probability distribution. Instead of PMF, which works for a discrete case, for a continuous random variable, we can find out the joint probability density function by differentiating the joint CDF with respect to dx and dy. And since this is continuous, the order of differentiation doesn't really matter. So we would have del square fxy by del y del x. Or in other words, we can write the CDF in this manner: minus infinity to y or minus infinity to x f of t comma s. Okay, so hi Dr. Lenina, I have just started the class. I hope you can hear me. I was just brushing up on the concepts which were discussed. I have not yet started discussing problems. So I hope you'll be able to catch up. Or shall I repeat this once again for you? Hello?
Good afternoon, Shreya.
Good afternoon, Dr. Lenina. Am I audible?
Yeah.
Okay. So I was muted, so you couldn't hear me. I'm sorry about that. So I was just brushing up the concepts which were discussed during week 5 lectures, and then I'll proceed to the problems. Do you want me to repeat? I just started about 10 minutes ago. So I'll just quickly recap. I was just discussing what we had learned. We had learned about random vectors and how previously we were dealing with one variables where for each omega we took a mapping from the sample space to the real line, and we were having the values of the random variables. Now if instead of one, if we take multiple variables together, then we would have a random vector. So a dth dimensional random vector would be a point in the d-dimensional space. Okay, and then we discussed how a joint CDF or cumulative distribution function should look like. It should be in the form probability x1 less than equal to x1 and x2 less than equal to x2, where x1 x2 can range between minus infinity to plus infinity. And the CDF should satisfy 3 important conditions. It should be non-decreasing, continuous from right with respect to both x1 and x2, and in a limiting sense, when both of these tend to plus infinity, the CDF should go to 1, and if either goes to minus infinity, the CDF should go to 0. And the third most important criteria was this one: for every ACBD, if we have probability A less than equal to x1 less than equal to b, and probability C less than equal to x2 less than equal to d, then this area should be positive, and this area can be represented by capital FBD minus FBC minus FAD plus F of AC. Okay, so this entire area shaded in purple, this area should be greater than 0. This is a very important condition that we should keep in mind. And then we learned how to represent or how to write a joint PMF in case of a discrete distribution. So we can write a PMF as probability x1 equal to x1, x2 equal to x2. This is the joint PMF. And if we are to find out the marginal distributions for x1, we have to take sum of the joint probability over all values of x2. Similarly, for x2, we have to take the sum of the joint probabilities over all values of x1. And to analogously, in a continuous setup, the joint PDF can be represented as the double derivative of the joint CDF or we can write the joint CDF in this manner: minus infinity to y minus infinity to x f of ts, where this is the joint PDF of x and y. And similarly, for marginal distributions, we instead of taking summation that we took for a discrete case, we have to take integral over all values of y to get the marginal of x, and to get the marginal of y we should take integral over all values of x. Okay, and this entire thing, minus infinity to infinity, the f marginal should, integral over all values of marginal should be equal to 1. So integral over all ranges of x and y, fx y xy should be equal to 1. So that is one of the criterias that should be. Yes, you have a question?
Not me, ma'am.
Okay, your hand is raised, so I thought. Aruna Ramados, do you have a question?
Hello, ma'am.
Yes.
Ma'am, sometimes you put some answers, but we can't be right. It is in the recommended text only. But the solution said the answer could be wrong. What's the reason, ma'am?
I did not get your question.
Ma'am, sometimes we refer and put the answer in the recommended text only. Okay. But in the solution set, we get the assignment marks as wrong. What's the reason for that?
So for your assignments, the solutions will also be shared with you. As far as I know, for weeks 1 and 2, the solutions have been shared. So have you checked your answers against those
Yes, ma'am.
solutions?
Yes, ma'am.
Okay, so if you find discrepancies over there, you can write to the NPTEL team, and I think they'll take care of that.
Okay, ma'am.
Okay. Thank you. Because the solutions are provided, and if you are not able to understand why your or how your solution is different, you can just put a mail saying how you've solved it and how it has been represented. But first, I think you should double check against the solution. There could be more than one way to arrive at a solution. So you check your answers against those, and if you find discrepancies, please write to the NPTEL team. Okay, all right, so I'll move on. So next we discussed what do we mean by independent random variables. So we can say that two random variables x and y are independent if and only if it's a necessary and sufficient condition that the joint CDF can be represented in terms of the marginal CDFs for all xy belonging to R2, that is in a 2D R space. In case of a discrete type variable, this means that the joint probability x equal to xi and y equal to yj can be represented as product of the marginal distributions for all pairs xi and yj. Similarly, for a continuous setup, it means that the joint PDF, so previously this one was the joint PMF written as a product of marginal PMFs. So similarly, in a continuous setup, we should have the joint PDF represented in the form of a product of marginal PDFs. Okay, and this works for two variables. But now if we have more than two variables, let's say we have n random variables, then those will be called mutually independent if the joint CDF can be represented as a product of the of the marginal CDFs. Okay, and similarly the joint PDF should be represented as a product of the joint PDFs. And another important theorem that was discussed was that if we have x and y.
Excuse me, ma'am.
Yes.
What is the difference between independent independent distribution and mutually exclusive distribution rule.
Okay,
Both seem to be same.
no, both are not same. So mutually exclusive means that x intersection y should be 0. Both cannot simultaneously happen together. But independent means this happening together would be this into this.
But in the formula, joint CDF equal to product of marginal CDF or joint PMF equal to product of marginal PMF for independent events, and it seems similar for mutually exclusive also. Here, product of the like previous slide.
This one?
This one, yeah. Here, pi I equal to k2 f of xi, k equal to 2 to n. So this also seems to be product of.
This is the criteria for independence. So when we write this thing, let's say we write fx1 x2, what we mean is that probability x1 less than equal to x1 and x2 less than equal to x2. So this and is essentially an intersection.
Okay, so this condition you have written for mutually.
This one I have written for mutually independent.
Independent,
So,
not
yes.
mutually exclusive.
No, exclusive means that both of these cannot happen together.
Yeah, I because of that word mutually, I got confused. I thought you have written it for mutually exclusive.
No. This is a very confusing thing. Lots of people get confused. Independence doesn't mean is not equal to exclusive. Exclusive means that two events will not occur simultaneously. So if I say that probability, if you throw two pair of, let's say I throw a pair of die, okay, this can range from 0 to 6 and this can also range from 0 to 6 or something like this. So if I say that x equal to 3 and probability x1 equal to 3 and x2 equal to 7, then that is a mutually exclusive event, because this together this will never happen.
Okay.
This was a cooked up example, but exclusive means that the condition, if we have an AND condition over here, two separate events will not happen simultaneously.
Okay.
So those are separate, exclusive events. But independence events, actually the criteria for independence is probability x1 equal to x1 and let's say y equal to y2. It is the same, so this is the criteria for independence. X1 equal to x1 given y equal to y2 is probability x equal to x1. So it doesn't depend on what the value of y is. This is what we mean by independence.
Yes, ma'am. Thank you.
Okay. All right. Thank you for this question. And also we discussed about IID random variables. So IID means identically distributed and independent. So if we have two, let's say if we say xy follows IID normal mu sigma square, it means that x also follows a normal mu sigma square, y also follows a normal mu sigma square, and they are independent. So if I have to write the fxy, the joint PDF of x and y, we can write it as fx into fy since they are independent. And the same form of the distribution we will be able to write as fx and fy. Okay, so this is what we mean by an IID random variable. So
one more question.
Yes.
Actually, CDF, PMF and PDF. CDF is defined for both continuous and discrete random variables.
Yes.
PMF only for discrete random variables.
Yes.
And PDF only for continuous random variables.
Yes.
Okay. Then when we write PDF, in terms of CDF, we take, PDF equal to derivative of
CDF,
CDF.
yes.
So how we can do that for continuous discrete
So
experiments? Discrete variables.
so you want to find out the CD. So for a if you notice, for a CDF, for a discrete random variable, your x values will be something here, x1, x2 and x3. So your CDF will be kind of a step function.
Yes.
Okay, and it will increase and go to 1, and this will be 0 for every
Yes.
any discrete thingy. But
Exactly.
for PDFs, you will have a continuous type of a thing. It will range from 0 to 1.
Yeah.
So if you have for here, at every given point, which is not a point of discontinuity, if you take derivative, it will be 0 only.
Yeah.
So your PMF, essentially, wherever the points of discontinuity are there, the probabilities are focused on that part. You cannot take derivative over these discontinuous regions, right?
Yeah.
But you can do it like for if I have to consider a PMF at PDF at, let's say, x1, we take what we take is a very small range along x1, and there we find out what is the probability density. So if your question is the form of the CDF will also differ based on whether the random variable is a discrete function or a continuous function. Okay?
Okay.
That will differ. And accordingly, if it is a continuous thing, you can take a derivative at all with respect to that function, and you can obtain the probability density function. But you cannot do so if you have a discrete case. There the mass will be concentrated across all discontinuity points.
Okay.
So here you will have something. PDF should always be right continuous. It shouldn't necessarily be left continuous for a discrete random variable. But for a continuous one, it will be a continuous. There will be no points of discontinuity. But for a discrete one, it will always be a step function.
Okay.
All right.
Thank you.
Thank you. So now we will just start with the problems. So the first problem is this. Let x and y be a two-dimensional discrete type of random variable with joint PMF this. Then what is the value of k? So first thing, we have been given, this is a discrete type of random variable. So x can take, let's say this is x and this is y. Okay, so x can take values 1, 2 and 3. And y can take values 1, 2 and 3. And this is how pxy will be these cells will represent pxy. Okay. Now for x equal to 1, y equal to 1, pxy will be k. Okay. So each of the cell will represent pxy. So this is p11, p21, x will be 2, y equal to 1. This is what? This will be 2k. This will be p31.
3k.
This will be 3k. Similarly, here we will also have 2k. Here we will have p13, 3k. p22 will be how much?
4k.
p32,
6k.
p23 will also be 6k.
6k.
And p33 will be
9k.
Now, if we remember, the summation over x, probability x equal to x, should be 1 in a univariate case. Sum of all probabilities should add up to 1. So for a bivariate case also, summation of x and summation of y probability x equal to x and y equal to y should be equal to 1. This should be satisfied. So here if I remember, I've put it in continuous form. Properties joint PDFs should satisfy these conditions. Similarly, joint PMF should also satisfy this criteria, that x equal to x, y equal to y should be greater than equal to 0 for all xy belonging to some space, and the summation over xy should also be equal to 1. So then if the total probability should be 1, then we should have sum of all these k's should be equal to 1. Therefore, k plus 2k plus 3k plus 2k plus 4k plus 6k plus 3k plus 6k plus 9k should be equal to 1. Solving, we would get k as
1/36.
yes, 1 by 36. Is it okay? Any doubt?
Okay.
Okay. So we'll move on to the next one. So here the problem remains same. K we have 1 by 36. Now we have to find out the value of probability 2 less than equal to x less than equal to 3 and y less than equal to 2. Okay. So then probability 2 less than equal to x less than equal to 3, y less than equal to 2. A discrete space, it means x can take values 2 and y can take less than or equal to 2. So y can take probabilities these and x can take 3, y1 plus x equal to 3, y equal to 2. Okay, so y less than equal to 2 means y can take value 1 and 2, and x less than equal x between 2 and 3 means y can take 2 and 3. Okay, so then x equal to 2, y equal to 1 is how much? 2k plus x equal to 2, y equal to 2, we have 4k
3k
plus 3k
6k.
plus 6k. So this will be 15k.
15k. Yeah.
So it will be 15 by 36.
36.
So the answer is 5 by 12.
12. Okay.
Alright. No doubts here? So we'll move on to the next one. So let's say I have a bag containing 40 blue marbles and 60 red marbles. I choose 10 marbles without replacement. This should be kept in mind at random. Let x be the number of blue marbles and y be the number of red marbles. Then find the joint PMF of x and y. Okay, so we have to find out probability x equal to x and y equal to y such that x plus y should be equal to 10. Okay, so then the denominator is, we are choosing 10 marbles. So total number of marbles will be 40 plus 60, that is 100. So we are choosing 10 from the 100 without replacement. So number of ways we can do that is 100C10, because this is without replacement. Okay, so with replacement we could have done it in how many ways?
100 PR.
100
Is
to
there
the
any-
power 10.
Any thumb rule to, decide whether to take permutation or whether to take combination.
Combination, it means what? So 100C10, actually it means what? It
Yeah,
means
any thumb rule we have, depending upon the problem statement.
so here we are selecting. So that's why we'll take combination. We are not arranging. It doesn't matter the order in which we are selecting. That's why we
Okay.
are taking combination.
Okay.
Okay, but if the order matters, then we would have taken a permutation if the arrangement would have mattered. And in case
Okay.
of with replacement, what we are doing, we are taking one, we are choosing one, and then we are putting it back. So here what we are doing is that we are out of 100 we are taking one, then out of 99 we are taking another, like that it is going, right? But here what happens, out of 100 we are taking one, again we are putting it back, so the next set also we are taking out of 100 only. So 10 times we are drawing from 100, so it
Okay.
becomes 100 to the power 10 in case of with replacement. But we are not doing with replacement, we are doing without replacement. So we
Okay.
choose 100C10. We can choose 10 balls from the 100 in 100C10 manners. Now 40 are blue. Let X is for blue. So we would have 40CX, and 60 are red. So from 60 we can choose this. But it is very important to note this line. This is the PMF, x plus y equal to 100, equal to 10. X can take values between 0, 1, 2. Y can also take values, but x plus y should not exceed 10. This is how we are representing a joint PMF of x and y. Essentially, this is a hypergeometric distribution.
Means?
So, were you taught about hypergeometric distributions?
No.
No, okay. So hypergeometric is this. These so NPCX into NQCY by N by C plus Y. This one. So hypergeometric. I think you've been taught in the previous.
Your voice is
okay. So hypergeometric distribution, it can be represented as k c small k n minus k c small n minus k by NCN. Okay, so we are, that is from a population of size n. Let's say this is a population. We are drawing samples of size n, and the population is divided into two parts. Let's say k and n minus k. So probability, we would have k small k number of samples from here, and the rest from the other is given by this thing.
okay.
Okay, so essentially it represents that k of small k samples with a certain feature, where we have dichotomous thing. We have two features, let's say. So from this total distribution, which can be dichotomously divided into two groups, the probability we have some number from one of the groups is given by
Why
this.
it's called hypergeometric?
This one I don't know why is it called hypergeometric. I will look into it and come back to you. It's a good, interesting question. It's called hypergeometric, but I don't know why. Okay?
Okay, thank you.
Okay. Okay, so let's move on to the next one. So let x and y be two independent discrete random variables with the CDFs fx and fy. So let's define z equal to maximum of xy and y equal to minimum of xy. And how can we write the CDFs of z and w? So CDF of z, this is z less than equal to small z. This probability maximum of x and y less than equal to small z. So now let's see this. So here we have one z, this can be x, this can be y, and this can be y, this can be x. So maximum of y and x here is x. So this should be less than equal to y, and maximum of x and y here is y. This should also be less than equal to z. So maximum of both is less than something. It implies that x less than equal to z and y is also less than equal to z. Only then the maximum will also be less than equal to z. Right? Suppose we had something like this. We had z here, x here, and y here. Then maximum of x and y will exceed z, right?
Exactly.
So for this to be less than equal to z, both an x and z should be less than y. So now and thing we can write it as intersection. So x less than equal to z intersection y less than equal to z. Now given we have independent random variables, this we can write as probability x less than equal to z into probability y less than equal to z. So this will be capital Fxz into capital Fy of z.
Yes.
Okay. This is how we can write the CDF of z given.
Is it z or x?
This is z. This is probably Fzz.
Capital x less than or equal to z, so it will be marginal distribution for x, no?
Yes, that is what I have written. This is the marginal CDF of x at z, evaluated at z.
Okay. So it is called evaluated at z.
Something like this. So if we have probability x less than equal to x, then we call it fxx. No. So if we have probability, let's say x less than equal to 5, we would do? We would put the value of x at 5 and get the CDF.
Okay.
Like that.
Yes.
Alright. So we have the CDF of z. Now what about CDF of y? So here we have to find out, CDF of w. So here w is minimum of x and y. So minimum less than equal to y means x and y can be here. Minimum of this thing should be less than y. So this case can also come here. So it's very difficult to, for minimum, this sort of a thing is very difficult to navigate. We have to take 3 different cases. So for minimum, what we will do, instead of taking less than equal to, we will find out the converse thing. That will make our case easier. So probability capital W greater than W means if this is W, x and y or y or x. So it means probability minimum of x and y greater than W. This means W has to be less than both x and y. This means that probability x should be greater than W and y should be greater than W.
Yes.
Okay, so similarly we'll have this one, x greater than w intersection y greater than w. So this will be probability x greater than w into probability y greater than w. So that we can write as 1 minus probability x less than equal to w
Yes.
into 1 minus probability y less than equal to w. So
Yes.
that we can write as 1 minus
Fx.
fxw into 1
Two.
minus fyw. So this we can write as 1 minus fxw minus fyw plus fxw fyw.
Yes.
Okay, so this is what, this is probability w greater than w. So then fww should be probability w less than equal to w. So this will be 1 minus probability w greater than w. So this will be 1 minus fxw minus fyw plus fxw fyw. So this essentially is fx of w plus fy of w minus
Fx.
fxw fyw.
Yes. Yeah.
Okay, all right, so now we'll move on to the next one. So here we have to find out probability x less than equal to 2 and y less than equal to 4. So that means probability x equal to 1, y equal to 2 plus probability x equal to 1, y equal to 4 plus probability x equal to 2, y equal to 2 plus probability x equal to 2, y equal to 4. So this will be x1 y2 is 1 by 12 plus x1 y4 is 1 by 24, x2 y2 is 1 by 6, again x2 y4 is 1 by 12. How much is it coming? Something 9 by 24 it should come.
Yeah. 9 by 24.
Okay. So the next thing is to find the marginals of x and y. How will you do it? Try it out.
Marginals of x and y. We can directly add the columns, no?
Yes, that's what we are going to do. So if we add up
The columns and rows. So for
columns
x,
and
we
rows.
add all the rows, and for y, we add all the columns.
Okay, so then probability, how should I write? Let's say we are finding out the marginal of x. So then
X equal to 1, x equal to 2, and x equal to 3.
So x equal to 1, x equal to 2, x equal to 3.
Equal to 3.
For 1, what will we do? We'll just add up 1 by 12 plus
By
1 by
12 plus
24
1
by
by
1 by
plus
24.
1 by 24.
1 by 6 plus 1 by 12 plus 1 by 8. So this will be,
This will be 4, 1 by 6.
this will be how much?
Mm,
3 by 8 something. And this will be how much? Something 11 by 24 I'm getting. If we add these three up, is it coming to 1? I hope you're getting this.
Yes.
So these values will give you the marginals of x. So similarly, find out the marginals of y.
Yeah, y equal to 2, y equal to 4, and y equal to 5. For y equal to 2, it is 1 by 2.
Okay.
And 1 by 24 plus 1 by 12 plus 1 by 8. Seven by 24.
7 by 24, it should be 1 by 4, no?
Oh,
This 24, 1 plus 2 plus 3. 6 by 24, that is 1 by 4.
okay.
Alright,
Yeah.
fine. Now we have the marginals. So the next question is this thing. Find the probability y equal to 2 given x equal to 1. So using the formula for conditional probability, what should we have? Probability, this is C. Y equal to 2. Okay, the previous one was marginal of y. Alright. Probability y equal to 2 given x equal to 1. This is how what? This is probability y equal to 2 intersection x equal to 1 by probability of x equal to 1. This probability y equal to 2 comma x equal to 1, probability x equal to 1. So x equal to 1 we had how much? 1 by 6. 1 y2 and x1 we had how much? This one.
1 by 12.
So it will be 1 by 12 by 1 by 6, that is half.
Half.
Okay. Similarly,
Yes.
if we would have had something like probability x equal to 2 given y equal to 5, we would have taken this value.
Yeah.
Sorry, given,
Mm.
oh sorry, here I wrote
Well,
it in, this
third
should
third
be,
column. Third column.
this should be 1 by 6. And here, sorry, one second, I'll color code it just for the sake of understanding. Okay, so if we had probability x equal to 2 given y equal to 5, we would have taken this one. Y equal to 5, the marginal was 1 by 4. So it will be y equal to x equal to 2, y equal to 5 by probability y equal to 5. Then x2, y5 is 1 by 8 by 1 by 4. This should
That
have
is
also
also
been half. Alright. Now we have to find out are x and
X
y
and Y
independent.
independent.
So how should we do it?
Their distribution, joint distribution should, joint mass function should be a product of
The marginals.
marginal.
Yes. So we have to see if it holds for all xy pairs. Alright. So now we'll just write down the marginals over here. So x equal to 1 was 1 by 6. X equal to 2 was how much? 3 by 8. And x equal to 3 was 11 by 24. Okay. So here y equal to 2 we had half. Y equal to 4 we had 1/4. And y equal to 5 we had 1/4. So for this thing it is holding. 1 by 2 equal to 1/6 into 1/2. 1 by 24, 1/6 into 1/4. Again 1 by 24, 1/6 into 1/4. But for this one, let's say probability x equal to 2, y equal to 2. This is 1/6. Now probability x equal to 2 into probability y equal to 2. This is 3 by 8 into 1 by 2. 3 by 16. Not equal to 1 by 6. So
They are dependent.
they are not, yes, they are not independent. Therefore, they are not independent.
Why we have taken only one case?
One is sufficient. No, if probability x equal to x, y equal to y should be equal to probability marginal into probability y equal to y for all xy.
Okay.
So if this should hold for each and every value pair. If for at least one
how
it is
we
not,
have selected x equal to 2 and y equal to 2 randomly?
I have not selected randomly. I checked, no. So for
No, no.
1/12,
I would have taken, I mean, x equal to 1 and y equal to 4 also, no?
yes, you could have taken, but that is satisfied. We have to check that this should be satisfied for all pairs. If for at least one we can find where this is not satisfied, which means they are not independent. If it would have been independent, then this would have hold true for all pairs.
My question is, how did you select x equal to 2 and y equal to 2? Why did you select x equal to 2 and y equal to 2 only?
I did not
Only-
select only. I can also proceed. But I stopped here because I found one contradiction.
No, what my question is, how you could
So I was going row wise. If you remember, so
Yeah.
what I did for 1/12 it's holding. If I have x equal to 1 and y equal to 2, this is 1 by 12. And this one into this one is also 1 by 12. So this is
Okay.
passing. For here also 1 by 6 into 1 by 4, 1/24. This is passing. This one also it's okay. But here I am seeing it's not okay. Similarly for this one also, if I go, it's not okay. 3 by 8 into 1 by 4. This will also not pass.
Okay.
This will
That's
also
what.
not pass. So I just stopped here because I need one contradiction to say that it is not independent. Had it been independent, this would have hold true for all pairs. But I found one which violating this criteria. So I stopped there and said this is not independent. I could go on, I could match all of these.
Okay, thank you.
Okay, here also it's not matching. 11 by 24 and half. This is also not matching, this is also not matching, this is also not matching.
Yes.
But if we just stop at one row, then we would be misguided.
That's what I mean. If we first row, first column, first row itself, if you would have taken, it would have satisfied, and
So
we would have declared that they are independent.
No, we cannot declare. That is what I'm saying. We have to check for every pair. For every
Okay.
combination, we have to check. If it holds true for all only, then we can say that it is independent. So that's why this for all is very important. It should hold for all values x and y can take.
Yes.
Okay. All right. This one. So let's say x and y be independent random variables where x follows a geometric p distribution and y follows a geometric q. Let z be x plus y. We have to find the PMF of z. So probability z equal to z equals to probability x plus y equal to z. Okay, so if x plus y, x can take, x is geometric p, so fx of x is how much, or rather if I can write it this way, probability x equal to x is p to the power x minus 1, 1 minus p to the 1 minus p, x equal to 1, 2 and so on. Okay, y follows geometric q. This means probability y equal to y equals to q to the power y minus 1 into 1 minus q, where y is 1, 2 and so on. Okay, so
Okay.
x plus y equal to z, small z, let's say. This one we can write as summation. Let us fix x at k. So y should be z minus k, and k can take values from 1 to z minus 1. Because if k is z minus 1, then y would have been 1. X plus y equal to z is satisfied. Okay, now this thing we can write as, this is comma, or equivalently we can write it as intersection. So now this is an independent random variable x and y. So we can write it as k equal to 1 to z minus 1 probability x equal to k into probability of y equal to z minus k, since x and y are independent. Okay, so now this one we can write as summation k equal to 1 to z minus 1 probability x equal to k probability y equal to z minus k. So we wrote the value of x equal to x. So instead of x we will be writing k. So this we can write as summation k equal to 1 to z minus 1 1 minus p to the power k minus 1 into p into 1 minus q to the power z minus k minus 1 into q, because x follows geometric p means probability x equal to small x is 1 minus p to the power x minus 1 into p. So for this means success probability at xth term. So before xth trial we had all failures, 1 minus p into to the power x minus 1, and at the xth trial we had success, so p. Okay, so this one, if we take pq and 1 minus q out, so this thing we can take it out. So what we can write it as, we can write it as p, this is not dependent on k, right? So we can take it out, pq this one 1 minus p to the power minus 1, by 1 minus p we can take out, and z minus 1 we can also take out, 1 minus q to the power z minus 1, then we would have k equal to 1 to z minus 1, 1 minus p to the power q into 1 minus q to the power minus k. Is it okay? So whatever is not dependent on k, we are taking it out. So this will be 1 minus p to the power minus 1, that we have taken out, and 1 minus q to the power z minus 1 also we have taken out, and pq also we have taken out. So whatever remains, this term is dependent on k. So we can write this as pq 1 minus q to the power z minus 1 by 1 minus p into summation k equal to 1 to z minus 1, 1 minus p by 1 minus q to the power k.
Yes.
Okay, so if this one we can write as pq 1 minus q to the power z minus 1 by 1 minus p summation k equal to 1 to z minus 1, 1 minus p by 1 minus q to the power k. So if we write it in this manner, this will be 1 minus p by 1 minus q plus 1 minus p by 1 minus q square plus dot 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 plus 1 minus p by 1 minus q to the power z minus 1. So this looks like a GP series. So then sum of this GP series,
1
if we have
minus a.
something, if we have like this, let's say AR plus AR square plus something. So this one we can write as A 1 minus r to the power, let's say r to the power n something, by 1 minus r. So this one we remember, sum of a GP series.
Yeah.
So same thing we'll apply over here. So we'll have PQ 1 minus q to the power z minus 1 by 1 minus p. A we will take common. So A is this one. Sorry, R is this one.
A is 1.
A is 1. So no, here we have A plus AR, something like this. So A is 1. Here we have. So no. 1 second.
A into r raised to 0.
A is 1 minus p by 1 minus q. This is A. This is AR. or let me write it in this manner. One plus r square plus r to the power n. This is 1 minus r to the power n by 1 minus r. Okay. So here 1 minus p by
The complete bracket is r.
yes. So if we take 1 minus p by 1 minus q common,
But the one is missing. No, r raised to 0 term is missing in this. So how we can compare to GP?
we can, and I'll tell you how. So here if we take this 1 minus p by 1 minus q as common, we
Common.
have 1
Exactly.
plus 1 minus
There.
p plus
Yeah.
1 minus p by 1 minus q to the power z minus 2.
Yeah. Now you can.
Now we can write it, no?
Yeah.
So this one we can write as pq 1 minus q to the power z minus 1 by, this one was what? 1 minus p into 1 minus p by 1 minus q. We had 1 plus 1 minus p by 1 minus q plus 1 minus p by 1 minus q to the power z minus 2. So this one was pq by 1 minus p 1 minus q to the power z minus 1 by 1 minus q 1 minus p 1 minus p by 1 minus q to the power
z minus 2.
This should be z minus 2 or z minus 1.
Z minus 1.
1 second.
R raised to n, no? In general, it is.
R s to the power n or r s to the power?
It's not n minus 1.
N
No?
minus 1. I think it's n minus 1. I'll just confirm 1 second. Geometric sum. So if we had have something like a plus ar plus ar square plus ar to the power n minus 1.
Yeah, n minus 1. We are starting from 0.
Yes. So that would be a 1 minus r to the power n by 1 minus r.
Yeah.
So here we are starting with z minus 2. So we'll have z minus 1.
Divided by 1 minus.
Yes. Divided by 1 minus
1. Yeah, after simplifying this.
So this one I have written it incorrectly. Yes, this is fine. So after simplifying this, what do we get? So 1 minus p is cancelling. Here we have pq 1 minus q to the power z minus 1 by this one. If we solve, 1 minus q and 1 minus q will be cancelled. We'll have p minus q. And we'll have 1 minus p by 1 minus q to the power z minus 1. Okay.
Here simplification, some issue.
What is the problem? So
yeah, this is 1 minus denominator. If you look at, it is 1 minus q minus 1 minus p.
1 minus q minus 1
1
minus
minus
p.
p. Okay, then
1 cancelled, p plus q minus. That is
yeah,
what is
p
coming.
plus p plus
This will be p minus q.
yeah, p minus q. Denominator will be p minus q.
Yes. So this
Okay.
is coming, and this 1 minus q and this denominator 1 minus q is cancelling out.
Then in the numerator also,
Numerator also, yes.
this 1 minus q.
So this will be pq by p minus q, 1 minus q to the power z minus 1, 1 minus 1 minus p by 1 minus q to the power z minus
Z
1.
minus 1
Hmm.
divided by okay, pq you have taken there. Now here 1 minus q z minus 1, 1 minus q z minus 1 minus 1 minus p z minus 1. Okay.
So now this one and this one will also cancel.
Okay.
So we'll
PQ
have pq by p minus q into 1 minus q to the power z minus 1 minus 1 minus p to the power
z minus 1. Okay. Now it's okay.
That's okay?
Yeah.
Alright. So now we'll move on to the next problem. So suppose that two buses A and B operate on a route. A person arrives at a certain bus stop in this route at time 0. Let x and y be arrival times of the buses A and B respectively. Suppose that x and y are independent random variables and their density functions are this. What is the probability that bus A will arrive before bus B? So we have to find out bus A arrival is x. We have to find out probability x less than y. Is it okay?
Yeah.
Okay. So we have to find out probability x less than equal to y. Less than y, strictly less than y. So we can write this as let us fix y at a given point. Okay. So what we'll have is that we can write it as probability x less than y given y equals to y into fy of y dy, where y can range from 0 to 4. This we can write by theorem of total probability. Okay.
Okay.
Now since x and y are independent, we can write this as 0 to 4 probability x less than y
Intersection probability.
So x given y is equal to x when x and y are independent. So we can write this. Now this one we can simplify. We have 0 to 4, y ranging from can range between 0 to 4. We should have probability x less than y and the marginal of y dy. So for this thing, whenever, so x can range between 0 to 3, and y can range between 0 to 4. So when the value of x is between 0 to 3, then sorry, here we have to write it as extremely sorry, here the value of x can range between 0 to 3. Okay,
The integral is with respect to x or y, dy or dx.
integral is with respect to y, but x can only take values up to 3. No,
Hmm.
oh sorry, my mistake, this should be integral is with respect to y only, this should be 4. All right, now here this thing we can break it up into two parts. When y is between 0 to 3, probability x less than y, so x can range between 0 to y, and we have okay, plus when x ranges from 3 to 4, when y ranges from 3 to 4, probability x less than y is
0.
1. X can range between 0 and 3, but y is starting from 3 to 4, so x is always less than equal to y.
Hmm.
So this probability is 1 into fyy dy. You understood?
Okay.
Okay, so now we'll just substitute. So 0 to 3, fx dx is 1/3 dx dy, plus 3 to 4, 1/4 dy. Fy dy is dy by 4. So here we would have 1/12, 0 to 3, 0 to y dx dy, plus 3 to 4 dy by 4. This one we would have as, okay, I'll write it here again, 0 to 3, 0 to y 1/3 dx, 1/4 dy, plus 3 to 4, 1/4 dy. This will be y by 3, 1 by 4 dy, plus 3 to 4, 1 by 4 dy. This will be y square by 24, 0 to 3, plus y by 4, 3 to 4. 9 by 24 plus 1 by 4. This will be 15 by 24. Is it okay?
Okay.
Now if this is a little difficult to understand, I'll also show how you can do it graphically. So let's say we have x here and y over here. Okay, so x can take values from 0 to 3. Y can take from values 0 to 4. So this one is my entire space. Okay, So this is 0, 3. This line is my y equal to x. So y less than x will be, sorry, x less, we are interested in x less than y. So that space is this one. Here you see x is less than y. X is 0, y is 3. So this point falls in this range. So this is the area we are concerned about. So required area is how much? This is 4 into 3 minus half into 3 into 3. 12 minus 9 by 2. This is how much? 24 minus 9 by 2. This is 15 by 2.
7.5.
7.5 or 15 by 2.
Greater than 1.
So required probability is 15 by 2 divided by the total area, that is 12. So we'll have 25 by 15 by
15
24.
by 24. Okay.
Okay. So if you have something uniform, if this method is difficult, then you can always plot it across graph, get the area which we need. So this one you understood, no? This is y equal to x curve, and these points, and take any point over here, this is 0, 2, where x is less than y. So this is falling in x less than y range. Similarly, if we would have wanted x greater than y, we would have taken this white part.
Yeah.
Okay. So you can also apply this method.
Yes.
Fine. So we'll proceed to the next one. So we have, let x and y be IID random variables with common PDF, this thing. Let u equal to x plus y, let v equal to x minus y. Then what is the joint PDF of u and v? So the way to solve this is as follows. So you have fx equal to 2 e to the power minus 2x is fx greater than 0. We have u equal to x plus y and v equal to x minus y. So this one first, what we'll do, we'll write x, that is old variables, in terms of new, that is u and v. So from here we can write x equal to u plus v by 2 and y equals to u minus v by 2. This is okay. Now step 2 is we should find something called Jacobian of the transformation. So what it means is that we have to find out the determinant of del x by del u, del x by del v, del y by del u, del y by del v. Okay, this is the Jacobian. So here we
From
have,
where did we come across this concept of Jacobian?
so while doing transformation, we have to adjust by the Jacobian thingy. Jacobian means determinant of del of old variables by del of new variables. This is something which we need. in order to go for these kind of any kind of transformation.
Okay.
Okay, so this is one step. If this has not been discussed, please note it here. If we have something like x plus y, x minus y, this to go from f of xy to f of uv, we need a Jacobian. All right. Now this one, so we'll have del x by del u. So del x by del u will be half. Del x by del v will be half.
Half.
Del y by del u will be half. Del y by del v will be minus half. So we would have this as minus 1/4, that is minus half. So step 3 is f of uv is f of xy into absolute value of Jacobian, and fxy represented in terms of u and v. So I can write it as fuv equal to fxy, and these x and y should be written involving u and v. So here we had fxy was what? Was independent, no? So we had fxx into fyy into Jacobian. So this one we had 2 e to the power minus 2 into x. X was what? U plus v by 2 into 2 e to the power minus 2. Y was what? 2 minus v by 2. And the Jacobian modular was this thing. So what we have is 2 e to the power minus u plus v into 2 e to the power minus u minus v into half. So this 2 and this 2 is cancelling. We have 2 e to the power minus u plus v. So or we can write it, if we open u minus v minus u plus v. So we have 2 e to the power minus 2u. Okay. Now we have to look at the range of u and v. This is the PDF, but it should hold true within some range of u and v. So let us now find out what is the range of u and v. So here x and y, wherever we had greater than 0, this would have followed. This PDF would have followed. So similarly from here we can see u plus v by 2 should be greater than 0. U plus v should be greater than 0. And from here what we have is u minus v by 2 should be greater than 0. So it means u should be greater than v. So then f of u
Can you
v,
come again here? U plus v by
so
x
here
greater than 0 means u plus v.
so we have written some fx and fy which is not 0, which implies that x and y must be greater than 0. So in terms of u and v, u plus v by 2 if it is greater than 0, then u plus v should also be greater than 0.
Yeah.
And u minus v by 2 should also be greater than 0, which implies u should be greater than v.
V.
Okay. So then fuv uv equals 2 e to the power minus 2u, wherever we have
U greater than.
yes, where we have
U
u
greater
plus
than v.
u greater than v, and u should be greater than 0.
0 elsewhere.
and 0 elsewhere.
Okay.
Okay.
Yes.
So this is the answer. All right. Now we'll go here. Let's see. So x and y be jointly continuous random variables. Which of the following is correct? So first, to find out whether they are independent, we need to find out the marginals. So fx of x is what? Summation over dy fxy xy. So it will be y ranges from 0 to infinity 6 e to the power minus 2x plus 3y dy. This one will be 6 e to the power minus 2x we are taking out, e to the power minus 3y dy.
By -3. No?
We'll do it now. So 6 e to the power minus 2x e to the power minus 3y by minus 3, 0 to infinity. So we would have 6 e to the power minus 2x by minus 3 e to the power minus 3y, 0 to infinity. So this would be 2 e to the power minus 2x. Are you getting this?
Yeah.
Okay. So we have the marginal of x. Similarly, marginal of y would be what? fxy x comma y dx, x also from 0 to infinity. So we would have 6 e to the power minus 2x plus 3y dx. 6 e to the power minus 3y we have taken out. 0 to infinity to the power minus 2x dx, which will also be 3 to the power minus 3y. Now fxx into fyy equals 2 e to the power minus 2x into 3 e to the power minus 3y equal to 6 e to the power minus 2x plus 3y, which is equal to fxy xy. Therefore, x and y are independent. So once they are independent, now we have to find out if, so this is true, x and y are independent. We have to find out if this holds true or not. Probability x greater than y equal to 3 by 5. So probability x greater than y. We have to find this out. So this one we can write it as, we'll fix y. So we can write it as, by theorem of total probability, probability x greater than y given y equal to y into fyy dy over 0 to infinity. Now x and y are again independent, so we can write it as probability x greater than y fyy dy. So then this will be 0 to infinity y to infinity 2 e to the power minus dx dx into 3 to the power minus 3y dy. Okay.
Okay.
So this will be how much? 0 to infinity 2 e to the power minus 2x by minus 2. This will be from y to infinity into 3 to the power minus 3y dy. So this will be 0 to infinity. We would have at infinity we had 0 minus of
E raised to minus 2y.
e to the power minus 2y. So plus into 3 e to the power minus 3y dy. So what we are having is 3 e to the power minus 5y dy. So it will be 3 by 5 e to the power minus y minus e to the power minus y. So this will be 3 by 5, 0 minus of minus 1. So this holds true. Probability x greater than y is 3 by 5.
Yes.
Alright?
Yeah.
Okay. So then we'll move on to the next one. So here we have let x and y be independent random variables where x follows binomial 2 1/3 and y follows binomial 3 1/2. Then probability x equal to y is how much? So x can take values between x follows binomial 2 to 1/3. So it can take 0, 1 and 2. And y follows binomial 3 to 1 by 3 with success probability half. So binomial can have, y can have 0, 1, 2 and 3. So probability x equal to y will be this one and this one. Sum. So then this will be probability x equal to 0, y equal to 0 and these are independent. So probability x equal to y will be probability x equal to 0, y equal to 0 plus probability x equal to 1, y equal to 1 plus probability x equal to 2, y equal to 2. Now we can write it as probability x equal to 0 into probability y equal to 0 plus probability x equal to 1 into probability y equal to 1 plus probability x equal to 2 into probability y equal to 2, since x and y are independent. Okay, so this one we'll just put formula. So this is, so if x follows binomial 2 comma 1/3, then probability x equal to x is how much? 2cx half to 1/3 to the power x, 2/3 to the power 2 minus x. So we'll just substitute over here. X equal to 0 means 2c 0, 1/3 to the power 0, 2/3 to the power 2 into y equal to 0 means 3c0, half to the power 0 to half to the power 3 plus 2c1, 1/3 to the power 1 into 2/3 to the power 1 into 3c1, half to the power 1, half to the power 2 plus 2c2 1 cube square 3 to the power 0 into 3c2 half square into half. How much are you getting this as? So this thing will be 2c0 is 1 into 1/3 to the power 0 is 1 2/3 to the power 2 into 3c0 is 1 half to the power 3 plus 2c1 is 2 into 1/3 into 2/3 into 3 into half to the power cube plus 2c2 is 1 1/3 whole square into 3 into half to the power 3. So this we have as 4/9 into 1/8 plus 4/9 into 3/8 plus 1/9 sorry 3/9 into 1/8. So this is 72. We have 4 plus 12 plus 3, that is 19/72 is the answer. Is it clear?
Yes.
Okay. So then this one. The random variable x has range 0, 1, 2 and y has a range 1 and 2. The joint distribution is given as follows, and which of the following are correct? Now we have to find out expectation of x and expectation of y. So we should find out the marginals. So here we would have marginal of y. Y equal to 1 probability is 0.5. Y equal to 2 probability is 0.5. Okay. Now marginal of x, this is y equal to 1, this is y equal to 2. Marginal of x will be 0.3, 0.2 and 0.5. So x is probability x equal to x is 0.3 when x equal to 0, 0.2 when x equal to 1 and 0.5 when x equal to 2. So then expectation of x will be 0 into 0.3 plus 1 into 0.2 plus 2 into 0.5. So it will be how much? 0 plus 0.2 plus 1, that is 1.2. Is it okay? And expectation of y will be how much? 1 into 0.5 plus 2 into 0.5, that is 0.5 plus 1, that is 1.5. So expectation of y equal to 1.5. This holds true. Okay.
Yes.
All right. So now we'll move on to the next one. So here we have x and y be random variables following uniform 0 1 independently. Then what is the expected value of expected value of the and variance of distance between x and y. So we have to find out the distribution of this thing. Okay, so now first things first, let us see what value this x and y can take. So x can range between 0 to 1, minus 1 less than equal to x less than 0 less than equal to x less than equal to 1. Y can also range from 0 to 1. So x minus y, it can range from minus 1 to 1. Therefore, mod of x
How
y.
did we get this?
So let's say x is 1 and y is 0. So then x minus y maximum will be 1. It cannot never cross 1.
Okay.
Now if you take the reverse thing, x is 0 and y is 1. Then it will x minus y will be minus 1. So it has to lie in this range.
Okay.
But since we are considering modulus, it should be positive. So the range of x minus y should be 0 to 1. This part is clear?
Yes.
Alright. So then while this is clear, we'll move on to finding out the distribution of x minus y. So let us assume let z equal to mod of x minus y. So probability z greater than small z equals to probability mod of x minus y greater than small z. So if let's say this is my modulo thingy, this greater than small z means that x minus y is greater than z and x minus y is less than minus z.
Here you are applying total probability.
No, here I am just applying modulus operation. So here if you see, if I have mod z less than equal to a, it means that minus a less than equal to z less than equal to a. Okay, so if I have something like mod z is greater than a, it means that either z is greater than a or z is less than minus a.
Okay.
So we are considering, so we are splitting this into two cases. Either this is greater than z. If this difference is greater than z, then modulo of this difference should also be greater than z. But if this difference is less than minus z, then modulus will be greater than z. Okay?
Yes.
So this we are splitting up. So once we have done this, we can write it as probability x greater than y plus z plus probability y greater than x plus z.
Yes.
Okay. Now since both of these, okay, I'll skip this. So not implies this should be equal to. Alright, so we have something like this. Now then from here we are going to apply the law of total probability. So we have probability x greater than y plus z plus probability y greater than x plus z. So this one, applying law of probability, we can write as probability x greater than y plus z given y equals to y into fyy dy. Now y can take range from 0 to 1 minus z, because x can take value, x should be greater than z and x should be less than 1. So if I put y equal to 1 minus z over here, then the value of, if I put y equal to 0, then we have x greater than z and it can go up to 1. It shouldn't cross 1, so the range will be 1 minus z. Okay. Similarly here also 0 to 1 minus z, probability y greater than x plus z given x equal to x into fxx dx. Alright, since x and y are independent, we can write as 1 minus z probability x greater than y plus z into fyy dy plus 0 to 1 minus z probability y greater than x plus z fxx dx. Okay, so now this thing we can write as 0 to 1 minus z probability x greater than 1 minus z, that so this will be y plus z to 1 dy, sorry, dx into fy dy is 1 plus, here also 0 to 1 minus z, this will be x plus z to 1 dy into 1 dx. Okay, so here we have 0 to 1 minus z, 1 minus y plus z dy plus 0 to 1 minus z, 1 minus x plus z dx. So here what we have, here we have 0 to 1 minus z, 1 minus z dy minus 0 to 1 minus z y dy plus 0 to 1 minus z 1 minus z dx minus 0 to 1 minus z x dx. This thing we can write as 1 minus z whole square. So this is dy, it will be y, and putting 0 and 1 minus z, we'll have 1 minus z whole square minus, we would have here y square by 2, 0 to 1 minus z plus again 1 minus z whole square minus x square by 2, 0 to 1 minus z. Okay, so here what we have is 1 minus z whole square 2 in minus 2 into 1 minus z whole square by 2. So we have 1 minus z whole square. Okay, therefore what we have is that probability z greater than z equals to 1 minus z whole square. Therefore probability z less than equal to z will be 1 minus z whole square. That is 1 minus 1 plus 2z minus z square. So we have 2z minus z square. So the CDF if z less than equal to z is equal to 2z minus z square when 0 less than equal to z less than equal to 1, and 1 if z is greater than equal to 1. Okay, so then this is the CDF. So then PDF is how much? If ZZ is tilde Z of FZZ, that is 2 minus 2Z, 2 into 1 minus Z, 0 less than equal to Z less than equal to 1. So therefore expectation of Z will be how much? It will be 0 to 1 z into FZZ dz. So it will be 0 to 1 z into 2 1 minus z dz. So this will be 0 to 1, 2 here we'll have z minus z square dz. So here we have 2 z square by 2 minus z cube by 3, 0 to 1. So we have 2 into half minus 1 by 3, 2 into so we have 1 by 3. Therefore expectation of z equals to 1 by 3. And also we were to find out variance. So then variance of z equal to expectation of z square minus expectation of z whole square. Now expectation of z square equals to 0 to 1 z square into 2 1 minus z dz. We would have 0 to 1 z square minus z cube dz. So we have 2 into z cube by 3 minus z to the power 4 by 4, 0 to 1, 2 into 1 by 3 minus 1 by 4. So this is 12, 2 into, so this is 1 by 6. Therefore we have 1 by 6 minus 1 by 3 whole square, 1 by 6 minus 1 by 9. This will be 18, 3 minus 2, that is 1 by 18 is the answer. So the final answer is this one, answer B. Is it okay?
Yes.
All right. So that was all I had for today. If you
Thank you.
have any questions, you can ask me. Otherwise, thank you for joining, and I'll see you next week.
Thank you.
Thank you so much.